So yeah, hello from my side, and thank you for the introduction. Today I'm going to present the results about our work, the Adaptive Decentralized Federated Gossip Learning for Resource-Constrained IoT Devices. This was a joint work with Navid Asadi, Benyu Chung from the Technical University of Munich, Christian Wiede from the Fraunhofer IMS, and Anton Grabmeier from the University of Duisburg. First, I will explain the motivation which led us to develop the proposed methods, which I will introduce afterwards. After introducing the methods, I will not only show simulations results, but also on-device hardware results, and end the presentation with a conclusion. First, let's have a look into the classical centralized federated learning. Here we have a central server which orchestrates the federated learning process and also performs the aggregation, which led to many advantages over classical machine learning, for instance, reducing the network load or to improve the data privacy. This also leads to the usage of centralized federated learning in IoT applications. However, the use of centralized federated learning has some drawbacks. For instance, if the central server fails, the federated learning process cannot longer be performed, and also the server cannot always be trusted. And one solution to this issue is the decentralized federated learning, where no central server is used. In decentralized federated learning, first, the training is performed on each device, and after training, the local models are exchanged. And after the models exchanged, the aggregation is performed on each device simultaneously. And this is the main difference between centralized and decentralized federated learning. But also, decentralized federated learning has still some drawbacks. For instance, the communication cost remains high. As we can see here, we chose the broadcast protocol. So each device has to send their local model to all other devices in the network. Also, the decentralized federated learning methods lacks investigations on resource-constrained devices, and the non-IID setting poses accuracy challenges. So to overcome these challenges, we first introduced a simplified segmented gossip protocol with quantization to reduce the communication cost, and afterwards extend the methods with adaptive learning methods to increase the accuracy. And lastly, we perform simulations and on-device evaluations. First, to decrease the communication cost, previously the segmented gossip approach with segmented pooling was proposed. Here, the local training is performed, and afterwards, each device divides the model into S segments. And after the segmentation is performed, each device requests each segment from R different devices, and afterwards pulling these R, each segment from the R devices. And only after each segment is received R times, the aggregation is performed. Due to the introduction of the replica hyperparameter R, the communication cost still remains high. This led us to our method, which was inspired by the previous method, the segmented asynchronous aggregation. And here we also perform the first two steps similar to the previous method. So we train our model and divide the model into S segments. But afterwards, we chose a different approach. We sent random segments to a random device in our communication network. And those three steps can be will be repeated until a threshold is met. And after the threshold is met, each the device performs the aggregation. Since we are choosing to send random segments to random devices, it may occur that segments are missing for the aggregation part. And if segments are missing, the missing segments are not aggregated, and in the next round, the missing segments are used from the previous local model while training. So since we are using the gossip protocol to reduce the communication cost, it was already been shown that the gossip protocol may result in slower convergence and lower accuracy. Also, we found that the plateau phenomenon may occur, and therefore we extend our method with adaptive learning rate methods to reduce the stallness and the plateau phenomenon. The first method we called ADASTER. In ADASTER, we adapt the learning rate after a given communication rounds. Here we call it ASTER, and if the threshold is met, the learning rate is halved. The second method we called ADA loss. Here we calculate the local loss with a local test data set, and if the loss is not decreasing for a given communication round, then the learning rate is halved again. First, we performed simulations results or simulation evaluations with a feed-forward neural network with 730 parameters with the MNIST data set in a non-ILD setting. And first, we analyzed the adaptive hyperparameter and chose 3 different settings for the ADASTER and ADALOSS method. And we found that the methods are working robust for different settings. Next, we choose to analyze different learning settings. Here in this method, in this analysis, we use the learning rate of 0.2, and initially we used 0.1. And here we can see in the green and blue line where we changes the learning rate. And here we can see that the accuracy is increasing after we are adapting the learning rate. Next, we performed on-device results with the MNIST data set with the same settings, and we were using a second data set, a gesture recognition data set, and we performed the evaluations on ESP32 microcontrollers, which can be seen here in the figure. And we also added a 16 and 8-bit quantization to further reduce the communication costs. Here in the results, it can quite clearly be seen that the usage of the quantization led to decrease of the communication cost and to increase the delivery rate. And it can also be seen that the other loss method is increasing the accuracy drastically, and similar results can be seen for the second data set. Yeah, to conclude the presentation, we proposed a more simplified segmented gossip protocol with adaptive learning rate and quantization, which not only reduces the communication costs, but also increases the accuracy, and performed evaluations on resource-constrained microcontrollers. For the future, a more rule-based segmented model exchange can be performed. Currently, we are using a randomized or random-based approach, and subsequently evaluations with further datasets and models should be performed, and the adaptive learning rate can also be optimized to get an even faster convergence rate. Thank you for your attention.